Mechanical Engineering. I welcome you all again for this guest lecture on role of computational mechanics in manufacturing process, having Dr. V. Dinakaran, Professor and Head, Center for Applied Research, Chennai Institute of Technology, Chennai, as our prime speaker today. Once again, I welcome you all. The very first part of this session, I request our HOD, Mr. S. Sundar Selvan, to render the welcome address among the gathering. Please, sir.
Yeah, very good morning to you all. It's my great pleasure to welcome all the dignitaries, and I welcome our management and our beloved principal sir, renowned vice principal ma'am, and dean of academics, and all learned faculty members, and our student friends, and especially resource person of today's guest lecture, Dr. V. Dinakaran sir from Chennai Institute of Technology. And once again, I welcome you all for the guest lecture on the topic of role of computational mechanics in manufacturing process. I once again welcome you all. Thank you.
Thank you, sir. Now I request Mr. S. Charles, Assistant Professor, Department of Mechanical Engineering, to introduce the chief guest among all the participants. Please, sir.
A very good morning to one and all gathered here. It is give me immense pleasure in introducing our chief guest, Dr. V. Dinakaran, Professor and Head, Center for Applied Research, Chennai Institute of Technology, Chennai, India. He expertise his skills in engineering, finite element analysis, and computational fluid dynamics, and composites, welding, additive manufacturing, and various other fields. Dr. V. Dinakaran is the author of abundant articles in peer-reviewed journals, as well as he is the author and editor of various handbooks in research areas, published with elsewhere, Taylor and Francis, and Springer. He is an associated editor in Journal of Robotics and Control and editorial board member in American Research Journal of Biomedical Engineering. Thank you.
Thank you so much, sir. Now I request our chief guest, Professor Dinakaran sir, to take over the session. Please, sir, and the stage is all yours. Thank you.
Yeah. So thank you so much. Thank you so much for inviting me to render a guest lecture on role of computational mechanics in manufacturing process. And primarily, I thank the management and principal, dean, HOD, and the organizers for conducting such wonderful guest lecture series. And also, I thank our management and principal, HOD, and dean for giving me an opportunity to present a lecture in Arasu Engineering College on behalf of Chennai Institute of Technology. And the role of computational mechanics in manufacturing process is one of the fast-growing field in the current scenario. So my lecture will be like this. So we are going to see what is the need to go for computational mechanics and how it is being different than the experimental analysis, and how to mimic the physical manufacturing process into a computational system, and how this will be highly useful in solving day-to-day problems. Okay. So these are the objectives which will be imparted on the participants to enhance their knowledge. So experimental versus numerical approach, and what is computational mechanics, and welding, and finite element analysis, additive manufacturing, and lattice structure simulations. So we should know what will be the role of engineers or researchers or scientists once they are getting into the field of work. So once they are entering into their job, their role may be to find out the solution for the physical problems. So physical problems is nothing but the problems which are arising from different areas. For example, if you want to save your country from the nation, then the defense will have some problems. If the human being are in need to live in the society comfortably, then they will have some problems. And if the industry is going to produce some materials or produce some products, then it will have some problems. So the problems which are being out from the industry or from defense or from society are called as physical problems. Okay. So the physical problems may be coming from these sources, and as an engineer or researcher or scientist, you need to find out the solution for these physical problems. Okay. So how to find out the solution for the physical problems? The physical problem will also be called as real world problems. Okay. So you people should understand what is physical problems primarily. The problem which are coming from society or industry or defense is called as physical problems. Okay. And in earlier days, the problems have the focus only has been given for the problems which are coming from defense. Okay. So you should know that the earlier days inventions and earlier days research were mainly focused on defense, or focused for defense purposes in order to save the country from the nation. And for example, so the aircraft has not been invented for transportation purpose primarily. They have been, or it has been invented only for serving the defense. How there is a very big interesting story behind the invention of aircraft, okay. And especially the jet engines. Okay. So in the earlier days, during the Second World War, the aircraft was using only the IC engines. So I hope most of you from mechanical engineering. So the internal combustion engine was only used in the aircraft. Okay. So what the Hitler wanted to do, Hitler wanted to win the race. For that, what he has done, he had called all the scientists, and all the scientists were put in a room. And in the earlier days, and now also, most of the Nobel Prize holders and most of the inventions have been done by Jews. Okay, so you know that Hitler is very much. I mean, he was with very much anger with Jews. I don't know what is the real fact behind that, but Hitler called all the Jews, especially the scientists, and they have been put inside a room, and only one instruction was given to them. When you come out from this room, you should come out with a solution or with an engine which should do or which should produce more thrust than the engine what we have in the aircraft. Okay, so this is the instruction put before them, and also he told that whatever you want, that will be supplied. Whatever you want, that will be given to you people. But if only you come out with the solution you will be allowed to live, else you will be shot out. Okay, so this is the thing which has been put on the scientists. Okay, like that. So we do not want to investigate whether the story is correct or not. But the thing is, the inventions have happened only for different purposes in the earlier days. Okay, so now the aircraft, the jet engine, what they have developed is being useful for human comfortably travel from one country to other countries in faster way. Okay, but nowadays equal importance is also being given for the societal problem also. And nowadays AEC and the central governments are taking much initiative to solve or to get the solution for the social problems. This importance was not given in the earlier days. Okay, right. The physical problems has to be solved, and for solving the physical problems, two methods are being used, are being familiar among the researchers. You can go for experimental analysis. You can go for experimental analysis, or you can go for modeling. Okay, so you will have problems in your hand. You're having problems in your hand. The problems might have come from society or defense or maybe from industry. To find out the solution for the problem, you need to go. You can use either experimental analysis or you can use modeling. Okay, so experimental analysis, there is a well-defined one. There is no substitute for experimental analysis. So experimental analysis means you have to construct the experimental setup. You have to construct the experimental setup. Then you have to run the experiments. You have to run the experiments. Then you have to read the data. You have to read the data. Then you have to analyze the data. You have to analyze the data. Then you have to come up with the conclusion how the parameters are varying. How the parameters are varying. Okay. So these are some standard procedures which are being followed while solving any problem using experimental analysis. Okay. So we have physical problem in your hand. Then the physical problem has to be, for solving the physical problem, you can follow either experimental analysis or you can go for modeling. If you are going for experimental analysis, first step is you have to construct the experimental setup. The second step, you have to run the experiments. Third step, you have to read the data. Fourth steps, you have to analyze the data. Then you have to come up with the conclusions, how you are conducting experiments in the laboratory classes. Okay. The second way, or the other method for finding the solution for the physical problem or real world problem is modeling. Okay. So modeling is purely based on some assumptions. Modeling is purely based on some assumptions. Okay. So at the end of the modeling, you will have some governing equations. The governing equations you will have. The governing equations may be either a differential equation or integral equation or integral differential equations. Okay. Then the governing equations has to be solved. The governing equation has to be solved. Okay. For example, if the governing equation is very simple, if the governing equation is simple, so if when you look into the governing equation, may be either if you look into as a differential equation, it may be either partial differential equation or ordinary differential equation. Ordinary differential equation or partial differential equation, right? And most of the engineering cases will have partial differential equations, right? Partial differential equation. How? Because in the ordinary differential equation, there will be a limited number of variables. So there will be only one dependent variables. Okay. But in partial differential equation, there will be more than one dependent variables. More than one dependent variables. Okay. And hence, in most of the engineering problems will have the partial differential equation as the governing equation. Partial differential equation as the governing equations. And if the partial differential equation, is very simple, if the partial differential equation is very simple, you can solve the governing equation with the known formula what you have learned from the mathematics. Okay. So, for example, if you have, well, let me take a simple governing equation. Okay, if you take d squared x by dt squared plus some y equal to 0, d squared x by dt squared plus y equal to 0. This is a simple governing equation. So you can this equation can be solved by using the standard mathematical formula what we have learned in the school days of engineering. Okay, and if you look at the simple equation, d squared y by dx squared plus x equal 0. So in right hand side, the equation is having only 0. Okay, then this type of equation will have only one solution, that is called what we call auxiliary solutions. There will have only auxiliary solutions. Okay. Suppose the equation is like this, d squared x by dt squared plus x equal to e power y or e power x. When something is in the right hand side, the equation and the solution for the equation will be the summation of auxiliary solution in the particular level. Summation of auxiliary solution in particular level. Then the particular level you can find out by you may use particular is equal to 1 by d into the particular e power x something. By substituting that, you can find out the solution for the governing equations. But as I said, in engineering, most of the equations are partial differential equation, and also especially the more non-linear, non-homogeneous second order partial differential equations. Okay. So most of the equations in engineering are non-linear, non-homogeneous partial differential equations. Okay. So to solve this partial differential equation, it is tough to solve by using the mathematical formulae what you have learned from the school days and doing your engineering. So for that, we need to find out the method, or need to find out some solution, or find out some way to solve the problems. For that, what we can do, we make use of the computers to solve the problems. We can make use of the computers to solve the equations. Okay. Then, when something or when some equations are being solved with the help of a computer, and then that type of modeling solution will be called as numerical solution or computational mechanics. Numerical solution or computational mechanics. Okay. So let me explain clearly. We will have physical problem in our hand. For the physical problem, or to solve the physical problem, we can use either experimental analysis or you can go for modeling. So modeling may be of two types. One is analytical modeling, another one is numerical modeling or computational mechanics. If in the modeling you will have a governing equations, that means the physical problem will be converted into a mathematical governing equation. Physical problems may be converted into a mathematical equation. For example, you consider a spring mass system. A spring, you have a spring, then a mass is hanging under that. Okay, then you can easily conduct experiments to measure the displacement when some force is applied. Okay, so this is one way you can conduct experiments analysis to find out the stiffness of the particular spring, or the maximum displacements you can find out by conducting experimentation. And parallelly, you can have the equation. So you know the equations, the governing equation for the spring mass system, d squared x divided by d squared plus kx. Okay, we have plus k by m into x equal to 0. So this is the governing equation for the spring mass system. Okay, so d squared x by d squared plus k by m into x equal to 0. This is the governing equation for the spring mass system. Parallelly, instead of conducting experimentation, you can conduct the you can solve the governing equation and you can apply the solution. If the governing equation is very simple, you can solve by using the mathematical formula what you have learned from the engineering school days. Then that type of modeling is called as analytical modeling. Okay, then if the governing equation is very complicated, you can't solve by using the formula what you have learned, then you have to make use of computer to solve the equations. Then that type of modeling is called as numerical modeling or numerical simulation or computational mechanics or computational modeling. Okay. So this is how the computational mechanics has evolved in solving the physical problems. Okay, so you should be clear. So either researcher or students and future you are going to serve for the society, you should know how the computational mechanics has evolved to solve the physical problems. Okay. Okay. Then I said, why we need to go for computational mechanics? I told how the computational mechanics has come out, how the computational mechanics has come out. And why do we need to go for computational mechanics? Why do we need to go for computational mechanics? Okay. The regular method of arriving the process parameters, like, so what might have been followed in the earlier days is, when you want to design a component, the component must have been designed. And upon testing, if it is found that the component is not satisfying the purpose, okay, you are designing the component, then you are testing for the purpose. If the component is not meeting your requirement, then what you will do, you have to throw out the components. And you have to modify the design. Then again, you have to produce the component. Then you have to go for testing. Upon testing, if the purpose is met, then you can go for compatibility. If the purpose is not met, then what you will do, then the component has to be thrown out. Then again, you have to go for design, then manufacture, then testing, then you have to analyze whether the purpose will be solved or not. So this process will take much more time, and it's a time-consuming process. Time-consuming process. Okay, and see, nowadays no one is having time. Neither industry or man or researchers, whoever it may be, they do not have time. They are always with the time constraints. They want the immediate results. If something is carried out at the moment, yes. Yeah, any disturbance, sir?
No, sir. You can continue.
Yeah, okay. So we do not have time. Okay. So for that, we need to have some methods. We need to have some better methods or better alternative to experimental analysis. Okay. And the computational mechanics will be one of the alternate methods. So the computational mechanics is not a substitute for experimental analysis. Okay, computational mechanics is not a substitute for experimental analysis, because seeing is believing. Okay, in explanation, whatever we are seeing, that is believing. But computational mechanics we cannot see. So most of the things are based on assumptions. Okay, so computational mechanics is an alternate method. It is an alternate method to find out the solution for the physical problem, but it is not a substitute method. Okay, so that you should clearly understand. Okay, so the computational mechanics will be used to avoid the experimentals what I was said earlier. Okay, so as I said earlier, you have designed the component, then you are manufacturing the component, then you are going for testing. Upon testing, if it is not met, the component will be thrown out. Then you go for redesign, remanufacturing, then you will go for retesting. Okay, so this entire process may be eliminated when you go for computational mechanics. Okay, so again, I am saying one point: the computational mechanics is not a substitute for experimental analysis. It is an alternate method. Okay, then how this alternate method or how computational mechanics is helping us to solve the physical problems. Okay, this computational mechanics will help you to do better experiments. How better experiments? So you can come up with a limited number of parameters. Or you can come up with a limited number of designs. The limited number of designs can be executed in the system, and the system you can test it, and whether the strength is achieved or not. Okay, once the strength is achieved, you can go for, instead of conducting large number of trials. Okay, so I told you, when you're going to design when you're going to manufacture new product, at least you might have 20 or 30 trials to properly bring out the products. Okay, when you use for computational mechanics, the 30 trials can be done in the system itself, and you can come up with five or six designs, and the 5 or 6 designs can be taken forward for physical manufacture. Okay, and after the physical manufacturing of 5 or 6 components, you can go for testing, and among which you can choose one of the best design. Okay, so by using the computational mechanics, we can do better experiments. See, almost 24 trials have been eliminated by following the computational mechanics. Okay, so let me explain this computational mechanics by using another one example. Okay, so what you will do, you are going to weld a component. Okay, so to weld the component, so you should have proper welding speed, welding current, and say another parameter. You may have is a stick-off distance, the distance between the plate and the welding torch. Okay, so this may be the variable parameters. Okay, so in order to have the full penetration or a very good welding cell, what you will do, you will fix the parameter upon trial and error basis. First, you will set up some current, you will set up some speed, then you will set up some stick-off distance. Then you will conduct trial. Okay, so upon conducting trial, then what you will do, you will cut a specimen. Then you will polish the specimen. Then you will etch the specimen. Then you will see in the macrograph whether the full penetration has been achieved or not, whether the fusion is proper or not. You will see. Okay, if the fusion is not proper, then you will eliminate the trial. Then you will increase or decrease or modify the current, then modify the welding speed, then you will modify the stick-off distance. Once again, you will go for conducting experiments. Then you will cut the specimen. Then you will see the macro structure, whether the full penetration is achieved or not. If it is not, then you will throw it. So like that, at least you would conduct 27 to 50 trials, minimum 27 to 50 trials, or more, large number of trials. You may say large number of trials to find out the parameter which may yield correct fusion. But this is possible. This can be executed for the traditional materials. So what are traditional materials like aluminum or stainless steel? You can conduct this one. You can use this procedure. Okay, because this stainless steel is low cost material, aluminum is low cost material. You can go with that. But nowadays we are using very costly material like aluminum, like titanium, inconel, zirconium. These are very costly materials. If you look at the titanium, so per kg you need to spend 7,000 rupees. Okay, so inconel also same. And when you look at the zirconium, it is costlier than titanium. But this material cannot be used as the procedure what I have said earlier. Okay, so this high cost material cannot be taken forward as like we have taken forward the traditional materials. So a new method is highly useful to reduce the number of trials. That method is computational mechanics. Okay, the computational mechanics will eliminate the large number of trials. Okay, so I hope you are very clear. Why do we need to go for computational mechanics? Okay, because there is a need to clarify the doubts. Everybody is saying that we are analyzing something. What for you are analyzing? The analysis itself, it is not believable one. Whatever you analyze, you go for section analysis, or you go for thermal analysis, you go for fluid flow analysis, whatever may be there, the analysis in itself cannot be a correct solution. Okay, you need to validate the results. You need to validate the results. I told you, the experimental analysis is believable one. So experimental trials are believable one, but computational mechanics is not believable easily. You cannot believe the computational solutions. The computational solution is only believable when it is validated. How it can be validated? The computer results can be validated by two things. One, by analytical solution. Second, you can validate with the computational solutions. Okay, so experimental solutions. Okay, the computational solutions can be validated by using either analytical solution or using experimental solutions. Okay. So you got to validate that. Without validation, the solution what you have found out through the computational mechanics is not at all believable one. Okay, so the people those are doing research also. If you simply you are saying that you are analyzing some fluid flow phenomena in ANSYS or ANSYS effects, whatever maybe, the analysis solution itself is not enough to go for publications. It's not enough to go for provide a concrete solutions. It needs to be validated. It ought to be validated with analytical solution or experimental solutions. Then only the results of computational mechanics are believable. Okay. Hence, I want to say the computational mechanics is not a substitute for experimental solution. It may be an alternate method to find out the solution for the physical problems. Okay. So, what is computational mechanics? Computational mechanics is a branch of applied mechanics which uses the knowledge of computer science and mechanics, which uses the knowledge of computer science and mechanics. And it is generally defined as it's the science of practice of obtaining approximate numerical solution using the digital computer. Using the digital computer is termed as computational mechanics. Okay. So computational mechanics may be used to solve the thermofluid problems, or used in thermodynamics, or used in electrodynamics, or used in welding and additive manufacturing. Okay, so it will take the particular name. If you use the science of or if you use the computational mechanics in the welding, then it is called as computational welding mechanics. If the computational mechanics is used to solve the structural problem, then it is called as computational structural mechanics. If it is used in if used to solve the fluid dynamics problem, it is the computational fluid dynamics. If you used to solve the thermodynamics problem, it is set as computational thermomechanics. If it is used to solve the electrodynamics problem, it is solved as computational electromechanics. Okay, the computational mechanics is a common name. It will take the name where it is being applied. Okay, like computational mechanics, computational electromechanics, computational thermomechanics, computational fluid mechanics. So it will take the particular name in the field of applications. So what are the steps to be followed when solving any problem using computational mechanics? Okay, so I already said you have to convert the physical phenomena or physical system into a partial differential equations. The physical system has to be converted into a partial differential equations. Then you have to use the physics. You have to use the physics to formulate the compliant systems. Okay, so you should know how to extract the physics from the mathematical equations. You have to extract the physics from the mathematical equations. Okay, so by utilizing that, you need to develop a mathematical model which is the replica of the physical model. That I said, we are having spring mass system. And when the spring is when you are applying some force on the mass, or when you apply some displacement on the mass, so how the system will behave, you have to bring a mathematical equation, or you have to system in terms of mathematical equations. So carefully it has to be done. If it is not properly converted, if the physical system is not properly converted into mathematical system, then your entire work will be waste. Okay, so it has to be carefully converted. Okay, then it has to be you have to go for discretization. Okay, so how to go for discretization? How to go for discretization? Okay, so I told you, we have governing equation in our hand. We have computer, but the computer does not know the governing equation. The computer knows zeros and ones. The computer knows zeros and ones, and we need to convert the governing equation into the understandable form of a computer. How it can be converted into understandable form? Then the computer can understand zeros and ones, or we can say the algebraic equations. The algebraic equations. Okay. Then the governing equation, which is in the form of partial differential or integral, whatever it may be, we need to convert the governing partial differential equation to algebraic equation, since the algebraic equation is only understandable by the computer. Hence, we need to have some methods. We need to have some methods to convert the partial differential equation into algebraic equation. Then some methods are being used that are called numerical methods. Okay, so what are these famous or standard numerical methods being useful in converting or doing discretization of the governing equation to algebraic equation are finite element method, finite volume method, and finite difference method. These are the three standard methods which are being useful in converting the partial differential equation into algebraic equation, which is the understandable form of a computer. Okay, so let us see what are these three methods: finite difference method, finite element method, and finite volume method. Okay. Finite difference method does not follow any physics. Does not follow any physics. How do I say it does not follow any physics? Or I can simply say, as an engineer, you should believe three equations. One is conservation of mass, conservation of momentum, and conservation of energy. So these three principles are essential, and the world is also existing because of only these three fundamental principles. If any system which violates these three fundamental principles will not be existing in the world, and it may not be existing in the world, and it may not be true also. Okay, so these three equations, three principles are equations: conservation of mass, conservation of momentum, conservation of energy. Without these three principles, nothing will be existing in the world. Okay, nothing will be. So, as an engineer, you should not believe the magic or whatever. Maybe some person is converting something into something, so you should not believe it. Because if these three equations are believable in the world, then how you can believe which is something being produced without consuming anything? Okay. Then how do I say the finite difference method does not follow any conservation principle? This finite difference method will not follow this conservation of mass, conservation of momentum, and conservation of energy. These three principles will not be followed by the finite difference method. The finite difference method simply uses the Taylor series expansion. It will use only the Taylor series expansion to solve the problems. Okay. So that we know, so 1 plus x whole power n equal to 1 plus something factor divided by some factor into 1 factorial with something you have in equations. Okay, that Taylor series expansions is being useful in being used to convert the governing equation into the algebraic equation by using finite difference method. Whereas in finite element method and finite volume method, this principle will be followed. This principle will be followed. Okay. So in finite element method, the entire domain. So because of the time, I am not going into detail. The entire solution will be divided into subdomains called the elements, and then the problem will be solved. Okay, there is a finite element method. So the entire solution will be divided or discretized into a finite elements, and it will be solved. Okay. Whereas in finite volume method, finite difference method, finite element method, you cannot see naturally the usage of conservation principles, but in finite volume method, you will be able to see through naked eye. How? Because you will, in finite volume method, the entire domain will be divided into some subdomains called as volumes. In the volumes, each volume will be checked whether the conservation principle is followed or not. Okay, so physically we will be involving in the process of checking that. So you can better experience the follow-up of a conservation principle, while using the finite volume method. Okay, so this is how the discretization is done and how the governing equation is converted into algebraic equations. Okay. So I said, so the results have to be verified, either experimental results or analytical results or both. If both are used to validate the solution arrived from the computers, then it is well and good. Or at least one of the results should be used to find out the solution for the problems. Okay. So in these two manufacturing process, I have planned to discuss. One is welding and one is additive manufacturing. So so these two manufacturing process will be concentrated on how the welding process is mimicked to get the to take the advantage of computational mechanics, and how the additive manufacturing can be utilized to get the solution of use the advantage of computational mechanics. So as I said, the computational welding mechanics, computational welding mechanics is the term when the computational mechanics is used to solve the problem of welding. Okay. So this is a weld pull. Okay, so when metal is subject to welding process, so a heat source, has moved from this end to here. It has moved from this end to here. While the heat is moving, it will be melted locally. It will be melted locally, and this zone is called as welding zone and fusion zone. Welding zone or fusion zone, and the metal will be melted. And this is one metal, and this is another material. So this metal is melted up to the melting point, and it will locally become as fluid. It will be locally become as fluid, and it will be merged together. And upon cooling, this will yield a homogeneous joint. And this is the laser power source, and this is a local weld pull. This is a weld pull. Okay, so this is a liquid weld pull. The liquid weld pull will be with a dimension of few millimeter, but it is a very complicated problems to analyze it. It's a very complicated phenomena. It's a very complicated phenomena, which cannot be easily solved. Okay, so in the regions near the fusion zone, what we have is the heat affected zone. Okay, and this is the unaffected base metal. Okay, so the power source, the heat is flowing from the top. Okay, so as I said, the same is a fusion zone, heat affected zone, is unaffected base metal, water maybe. So at the fusion zone, the temperature, when you look at the temperature will be high at the fusion zone, and it is brought up to the molten temperature. There's melting point. So molten metals will be it will be elevated more than the melting point of the particular material, and then the temperature will keep on decreasing until the base metal or pure metal. Okay, see, the temperature is decreasing linearly from the weld coal to the pure metal. Okay, so a lot of parameters are the reason teaching this fundamental is you should to use the computational mechanics. You should know the fundamental physical system clearly. Okay, the physical system should be understood clearly. Okay, then only see what you are going to do while using computational mechanics. You are going to convert the entire physical system into a governing equation. Okay, so how the governing equation can be achieved is it is not easy process to get the governing equation from the physical system. If only you clearly understand the physical system or physical principles, you will be able to convert the physical system into a governing equation. For that, you should clearly have the knowledge. Okay. Okay. So the arc efficiency. Okay. See, whatever be the heat, may be the heat which is falling on the material, or whatever may be the heat which is coming from the power source, may not be properly utilized to make the material. Always there will be losses. What are the losses? The losses may be due to the conduction, maybe due to the convection, due to the radiation. Okay, so you have to clearly understand whatever the heat which is coming out from the power source may not be utilized or cannot be utilized to achieve or to melt the material. Okay, always there will be losses. The losses may be due to the modes of heat transfer like conduction, convection, and radiation. So in order to account the losses, you need to bring the efficiency. Hence, you have to use the efficiency called arc efficiency to account the useful heat. Okay, so if the 100% is the total heat produced, 100% total heat produced, then you have to deduct, or you have to subtract the losses. Okay, Q is the heat transfer to electrode. Okay, electrode from the welding arc. Then it's a Q is the radiation and convection losses, and N is the proportion of the heat output from the arc column that is transferred into the workpiece. Okay. QW is the rate of heat absorbed by the workpiece. Okay. So these are the losses. And only this efficiency will be utilized to convert the molten pool into the absorbed by the material to for converting the molten pool. Okay. So this is in terms of the electrode used in the welding may be either consumable electrode or non-consumable electrode. Okay. So if you use non-consumable electrode, this is the loss. If you use consumable electrode, so that will be eliminated, and losses will be like the efficiency can be calculated like this. Okay. And also there are different parameters, a lot of parameters in the welding. So like arc heights or the distance between the torch to the mortar to the plates. Then welding current and polarity, and welding speed and gas. What is the gas you are using, and what is the diameter of electrode, and what is the preparation and contamination. So Arun sir, so how long I can go, sir?
Sir, for your sir.
For my convenience. Okay. Right, sir. Right. So okay. So shall I take another 25 to 30 minutes? Will it be okay? Okay, fine, sir. Okay. So these are the welding parameters. Okay. So welding parameters. Oh, so like I told you, welding current and polarity. Okay, welding current. Okay. So how the direct current electronegative, direct current electrode positive, and AC alternating currents. Okay, so these are the three standard what we call welding polarities being used while welding process. Okay. So this is being chosen upon how the weld pool has to be prepared. How the weld pool has to be prepared. So if you want to have the the deep weld pool, then you have to use a direct current electronegative. Okay. So electronegative means the electrode will be acting as a negative. Okay. So then the DCEP, direct current electrode positive. So electrode will be acting as the positive terminal. That will be acting as a positive terminal. Okay. And so this you can have the shallow penetration, shallow penetration. So when you want to have the cleaning action like that, when you want to weld the aluminum material, then essentially there you need to have the acid cleaning action. The reason for having the acid cleaning action is there will be some deposition of material while welding the aluminum. So in order to clean the electrode, then you have to go for actually alternating current. Then aluminum can be welded properly. Okay, so you have to properly choose the welding current polarity during welding process. Okay. Effect of welding speed. Okay. So welding speed plays a major role in the welding. Okay. So see, one thing you have to understand: the amount of energy will be same. There will be no variation in this. Okay. The welding speed can be used as variable parameter to meet our purpose. Okay. If you increase the welding speed, then it will reduce the heat input. Okay. See, when you increase the welding speed, the heat input will be reduced. When the heat input is reduced, the heat falling on the material for the particular area will be very less. Then the melting will happen very less. Accordingly, you will get the depth of penetration. Okay. Then if you want to if you are reducing the welding speed, the heat input falling on the particular area will be high. If the energy falling on the material is high, certainly more material will be melted and the fusion can happen properly. Okay, so the welding speed has to be chosen properly. Okay, welding speed has to be chosen properly, and you need to spend lot of time to fix these parameters. And these parameters can only be fixed out upon trial and error method. Okay. Hence, this trial and error method can be effectively divided up or can be thrown out by using computational mechanics. Okay. Then shielding gas. See, when you use the titanium or inconel or zirconium material, it is highly reactive to the environment. Okay, so that has to be properly the weld pool has to be properly protected. The weld pool has to be properly protected. In order to protect the weld pool in a good way, then you have to create an inert atmosphere. The inert atmosphere can be produced by the utilization of shielding gas. Okay, so the shielding gas will also have some effects. The type of shielding gas what you are using to protect the molten pool, and the amount of gas what is the amount of gas you are using to product the molten pool, also playing imaginary. Okay. See, as I said, the metal is locally melted. When the local metal is locally melted, it will be as liquid. It will be as liquid. When you make the airflow more, or when you increase the when you give the a high amount of airflow, this airflow may create a turbulent action, because of which the molten pool may be disturbed. The molten pool may be disturbed. When the molten pool is being disturbed, it is not a very good thing to achieve proper penetration. Hence, the welding speed has to be proper. The flow of gas, the amount of gas should be chosen properly. The type of gas should be chosen properly. If they are not properly chosen, it will also have some effects. Okay. Then electrodiameter and preparation. Okay. So electrodiameter, the angle. So mostly, commonly 30 and 120-degree angles are found to be good during welding upon the previous experimental trials and the published literature. Okay. So this depth width ratio and penetration can be fixed or can be decided by carefully choosing the electrodiameter also. Okay. So these are the parameters which are needed to be decided upon a trial and error method, for which you need to spend a lot of time and energy if you do not follow the computational mechanics. So welding is a multi-physics problem. It's not an easy problem. Welding is a multi problem. It involves fluid flow, it involves heat transfer, it involves suction problems. Okay, so I said, it's a locally it becomes liquid, even though it exists for a few seconds, and it is of few mm. It's a very complicated phenomena. It's the welding phenomena. So it's a multi-physics problem. So a lot of forces are coming into effect. Electromagnetic force, Lorentz force, Marangoni effect. So a lot of forces, earth pressure will be coming into effect too. It's okay. So a lot of physical phenomena are getting involved in the welding process, by which it is a multi-physics problem. So it's the same. I said, so it involves a thermal analysis. It involves thermal analysis. It involves mechanical analysis. It involves metallurgy. It involves fluid dynamics problems. Okay. So all the phenomenon has to be considered properly. All the phenomena have to be considered properly to properly solve the problems. Okay. So the microstructure may be altered if you are not properly choosing the parameters. Metallurgical effects may not be proper, and the strength of the weld may not be good. The strength of the weld may not be good if the proper parameters are not properly chosen, and if the fluid problems, if the molten pool is disturbed, and the stress measurements, residual stress. So thermal analysis, that means the heat transfer. Heat transfer has to be properly analyzed. Heat transfer. Okay. So how the what we call the losses, how the losses are being useful. That also has to be studied while analyzing the welding problem. Okay, so hence welding is a very big multi-physics problem. So all the concept has to be properly understood before converting the physical system to a mathematical system. Okay, so different regions, how the forces are being effective in the welding. So how this structure of the weld pool will be? Okay, as I said, so it's a local weld pool. It's a local weld pool. So it will move in this way, this way. Okay, heat source will move in this way. As a weld pool. So as I said, it will have the Marangoni force. It will have Lorentz force. It will have buoyancy effect. The arc pressure will be influencing the molten pool. The aerodynamic drag force. The aerodynamic drag force will also be influencing the molten pool, and the laser losses, radiation from the plasma. Okay, so all the losses will also be coming in effective, and these are the things will be designing the structure of the building. How the structure of the building. So, what are the specific issues during welding? So, during welding, fusion zone will be formed. Flow will be taken place inside liquids, and fusion zones will be solidifying. Okay, so the time steps to be adapted to handle the phase change properly. I told physically, when heat is falling on the material, it will be conducted physically. Okay, but when it needs to be expressed in terms of mathematical equation, how the heat is conducted in the material has to be mimicked into in terms of mathematical equation. And why the computer solves the problem, the time has to be properly defined. The time steps have to be properly designed or defined to take care of the concepts what happens in the physical process. So in physical process, we know how we have thermal conductivity. Thermal conductivity, we know that the ability of the material to conduct the heat. So the watt per meter square Kelvin. Okay. But in the computer, you will say thermal conductivity. Apart from the thermal conductivity, that is one thing is called alpha. Okay, alpha is the thermal diffusivity. Alpha is called as thermal diffusivity. Okay, so how fast the heat is penetrating the material is defined by alpha. Okay, so this fastness, this ability of the heat to penetrate the material is understood by the physical process. But how to impart on the computer or how to impart in the numerical simulation to take care of this ability of the material to penetrate the heat. So for that, the time step will play a major role. Okay, so the time step has to be properly defined while solving the problem. So there are a lot of cases based on the time steps while solving the computational analysis, like a explicit method, implicit method, and Crank-Nicolson method. Okay, so these are the three standard methods to take care of the time steps. Let me repeat the methods: explicit method, implicit method, and Crank-Nicolson method. These three are the standard methods which are having the ability to take care of the time steps. Why I need to take care of the time step? If only you properly take care of the time steps, you will be able to incorporate or you will be able to mimic the physical process, what happens when you are doing welding or whatever may be the process. Okay, so you need to take care of this. And also the stability. I said, explicit, implicit, and Crank-Nicolson method can be effectively chosen by the help of stability criteria. There is a concept called stability criteria. It is a very, very important one. The stability criteria will help you to choose this explicit, implicit method, and Crank-Nicolson method. So these three methods, stability criteria, and time steps, these three are very important while solving the problems using computational mechanics. Okay. So then multiple driving forces. I told you, multiple driving forces. Buoyancy force is coming into effective, or pressure is coming into effective, aerodynamics, drag force is acting on that. So a lot of things are happening. So that they have to be properly taken care. Then, grid independence and time step independence are important. So grid independence and time independence. So what are that? Okay, what are that? I told the domain has to be split into uh, different finite volumes or finite elements. You have to divide that. Okay. Then the what the things will be solved is while considering the finite element method, the solution will be available only at the nodal points. The solution will be available only at the nodal points. Okay, so the nodal points when you divide the domain into number of elements, when divide the number of elements, then the two elements are meeting at a point. That point is called as nodal point, and we will or the software will solve the problem at the nodal point. The solution will be available at the nodal point. Solution will be available at the nodal points. Okay. Now you can divide the domain with more number of elements, or medium number of elements, or very less number of elements. Okay, so these elements can be chosen. Number of elements can be chosen, or number of elements, or it will also be set as meshing or discretization. Okay, you can name it like this. You can divide the number of elements, or it may also be called as meshing or discretization. This meshing or discretization will be preferred based on the thing what we are going to measure, or based on the physics what we are going to import on the particular problems. Okay, so let us consider. I'm going to apply a heat in this portion. I'm going to apply heat in this portion. We'll apply heat in this portion. The heat, the heat transfer more dominant for the particular area around this portion than the ends. Okay, so let me you clearly understand. I am applying heat here. The applied heat may highly influence for certain portions than the far away ends. Okay, then the area where the heat will be highly influencing will be having more measures than the area where it does not have influence. Okay, so this is called meshing. Okay, this is called meshing. Then what is grid independence and time independence studies? That means when you change the mesh size, the solution will not vary. You have to come to a point where the solution will not vary even if you change the mesh size. So that study is called grid independence study. Okay, the point, or you will come to a point where the solution will not change even if you change the mesh size. So that is called a grid independence study. Okay, so that has to be ensured here. Then conservation equations. I said three conservation of mass, momentum, and energy. These are the important conservation equations. The conservation equations are already existing. Already the scientists have found out that conservation of mass, momentum, energy are available in the textbooks, available in the literature. Then what is your role? What you are going to do? Okay, so the given equations, conservation of momentum, this rho into dou A by dou T plus OV bar into del V and minus del pressure and mu del plus the particular equations. Okay, this is a velocity. Okay, this is a pressure. Okay, this is the rho is a density we have, and this is one term called source term. Okay, so this is called tension. This is called conductive, and this is pressure. Pressure gradient. Okay, this is the diffusion parameter. This is a diffusion gradient, and this is called source. Okay, so this equation is available in the software. This equation is available in the textbooks. And what you are going to do while you use this equation in computational mechanics is you can alter this equation. You alter this SU. The source term can be altered. The source term can be altered based on your physics or based on your parts. You can modify this particular term, and this particular term can be, this equation is available in the software, and this SU can be defined as a user-defined equation or user-defined function in the software by you, and the problem can be solved by any analyzing softwares. Okay. So it's a conversion of equation for thermal field. So thermal field, this is nothing but Fourier's law of heat conduction. This is nothing but Fourier's law of heat conduction. So this equation you might have studied in the heat transfer itself. Heat transfer itself in the heat transfer, heat and mass transfer. First unit itself, this equation is given. Then how this equation is being used for researchers to solve the problems? Yes, only the ST terms, the source terms. Only the source term has to be modified. So I told the governing equations for free flow. Okay, so this equation, this is the same equation. So I have expanded here the same equation, which is motor. It's given here, given free flow. So I have expanded this, and the different directions, the x direction, y direction, z directions, the source term. The source and AC, the SU has to be defined based on the columns. So such as pressure gradient, if you include the pressure gradient, then minus dou by dou x, you have to replace the SU by minus dou by dou x. If you want to include the body force, then you have to replace the SU with these equations. If you want to include the porosity formation, if you want to have the porosity formation for phase change, then you have to substitute, or you have to replace this SU with this one. Okay, let me clearly mentioning this equation is already available in the software. The only thing is you should know how to make use of other parameter, other equations, or other physics to replace this SU. So I have tried to weld a titanium welding. So what are the difficulties what are the standard methods used to weld the titanium? Electron beam welding, laser beam welding, and laser beam welding, then plasma arc welding and convectional optic welding. These are the methods being useful in titanium welding. What are the difficulties are? Titanium is highly reactive material, and it is easily they can combine with nitrogen and oxygen. Hence, carefully the precautions have to be considered during welding process. So plasma arc welding. So it's a plasma arc power source. So the workpiece acts as positive, and the electrode acts as negative. So DCEN, direct electronegative, is being mostly used in the plasma arc welding process, and the heat will be flowing from the torch to the workpiece. So the experimental setup. So experimental setup has been used, which is available in the National Institute of Technology, Tiruchirappalli, has been utilized to conduct my experiments. And so these are the welding parameters which has been used to conduct the physical trials. Okay. So I told the molten pool has to be properly protected. Properly, if it is not properly protected, it will be reacting with the environment, and that will not produce the sound weld. Hence, a trailing shield has been designed. It's a new trailing shield which is going to be patented soon. These are new training field we in our lab with the co-research, with the help of my guide, Dr. Shivashanmugam and Dr. Sanganayan Sami, and my co-researchers like Dr. Karporaj and Dr. Stephen. So we have developed this new trailing shield, and which is going to be patented soon. And this new trailing shield has been effective to produce a very good sound bed. Okay, so after using the trailing shield, we have got a very good sound weld. Okay, so before using trailing shield, we got this one. So this welding color is not at all allowed, and this is the quality weld which is accepted by the research community. So we have chosen 3 parameters: welding current, welding speed, and arc length has been fixed as 8 mm. So 50, 55, 60 amps current has been chosen, and 250, 270, 300 mm per minute welding speed have been chosen for the welding details, and these are the weld beads obtained through the welding process. Okay. And during the welding, the temperature has also been measured, because during welding, if you cannot measure the welding temperature at the weld pool, because it will be very high temperature. So what we have done, we have chosen around 6 cm from the center of the weld pool, and we have used IR thermometer to measure the temperature. Okay. So after welding, so we have cut the specimens. We have got the specimens, and we have seen the penetration of the welding. Okay. Then we found that the 250 60 amps current to 60 amps current and 250 amps welding speed has yielded a full depth of penetration. Hence, that parameter has been chosen for what we call creating the butt weld joint. Then we have measured the stress by using cold drilling method. So how these stresses are produced in the welding is, when the metal is heated, the molecules will move away from the molecules will try to move, because according to the kinetic theory of gases, when something is heated, the molecules will get some extra energy, and the molecules will try to move away, or will try to run faster. Okay, when the molecules are trying to run faster and faster, so say, because say this is the weld pool, so this when molecules are heated, the molecules will have more energy, and it will try to escape from there, and some of the molecules go, and after some distance, this molecules which are here may not feeling the heat, and they may not be moving. They are not moving away. Okay, so hence this moving particle will try to push this molecule which are stationary. So then there will be a fighting between these moving particles and the molecule which are stationary. Because of that, a stress will be existing. That stress is called thermal stress. Okay. So we have measured the thermal stress also. So then this distortion. See, if you look at the figure. So one side you are able to see the distortion. Okay, the distortion also has been measured using the CMM machine, which is available in the Defense Research and Development Organization in Bangalore, GTRE, Gas Turbine Research and Development, Gas Turbine Research and Establishment. Okay, so this also is a very costly machine. So XRD resolution measurement equipment, which uses the Fragg's law to find out the stress in the particular component. Okay, so this is also available in the GTRE DRDO lab in Bangalore. So now we have understood the physical process. And how the physical process can be used to convert the computational physical process has to be converted into a governing equation. Okay. So for that, so in welding, the heat is involving. Okay, then how the heat will be flowing to the material? How the heat will be flowing into the material? Okay, so that has to be said. Okay, so heat is coming and it is flowing to the material, and what shape the heat will go into the material? Okay, so that has to be predicted properly. So the model which explains the flow of heat into the material is called heat source model. Okay, then the heat source model has to be carefully chosen. So already the available heat source model, double ellipsoid heat source model, conical Gaussian heat source model, and modified thin heat source model are available in these literatures for welding. Okay. So this uses the equation. The double ellipsoid heat source model. This heat source model is like this. The person Colton said that the heat is flowing in the material in the two ellipsoids. In the form of two ellipsoids, the heat is flowing into the material. He said. Okay, and the equations are different like this. And C.S. Wu, who is the professor in China, has said that the heat is flowing like a cone into the material. The heat is flowing cone in the material. He said that. Okay. And another person, he modified the heat source model, and he told that it will not go like a cone. It will go like this truncated cone. It will go like a truncated cone with the material. Okay. Then, in our research, we found that the weld shape, the weld pool shape is not either a cone or double ellipsoidal. We found that this is like a parabola. We found that it's like a parabola. Okay. Then we developed a new heat source model. And the new heat source model we have developed by using a parabolic Gaussian heat source. It's a parabolic Gaussian heat source or parabolic Gaussian distribution has been utilized to develop the heat source model. Okay, and the heat source model, this is the distribution parameter R naught of z is equal to a z square plus b. The distribution parameter equation, we have assumed this equation, and we upon solving this equation, we found that the parameter of a and b, the a and b are the constants. A and b and constants are constants have been found out by solving these equations. By solving this equation at the top and bottom. Okay, and see, this is a parabola. Okay, in the parabolic distribution has been used to define or to mimic the physical. This is physics, right? This is a physical system. And I am converting the physical system into mathematical equation. So I developed a mathematical model called Dinakaran's model. So in my name, it has been published and it is available in the literature. And the Dinakaran's model has been developed. And the Dinakaran's model has been derived by using the triple integral, and this is the equations. What we have developed to represent the Dinakaran heat source model. So this is the equation, and where the AV is represented by this equation. Okay. So this is the heat source model, which will be the replica of the physical process. So we use final console, multiphysics, one of the final software to solve the equations. Okay, so what I have done, so I told you earlier, so this equation is available in all the softwares, all the analysis softwares. The only thing is the source term. I told you, the source term. So here QV is the source term. The QV source term is going to be replaced by this equation. This equation is going to be substituted in the terms of in the place of QV, and this equation has been solved by the console multiphysics softwares. And I want to substitute the boundary conditions. So the equation has to be solved by using boundary conditions. So we have used the boundary conditions to define and the losses. It's a natural boundary condition. These are the essential boundary conditions to solve the equations. Okay, and we have developed a new heat transfer coefficient, so Nusselt number. So we have found out the Nusselt number correlation from the standard data book, and we found out the Reynolds number. We derived in Reynolds number, Brandel number, and we from the Nusselt number we found yes a new heat transfer coefficient. A new heat transfer coefficient. Okay, the heat transfer coefficient H in terms of watt per meter square Kelvin, and the thermal conductivity will be in terms of watt per meter Kelvin. Okay, so the heat transfer in terms of watt per meter Kelvin has been derived by using by having the correct Nusselt number correlation. So this has been brought out from the box I told you earlier, trailing seal. From the trailing seal we have derived this, and the final mass I told you, these in the center heat transfer will be here in the gradient the heat gradient will be high at the at this region. When you move away from this center, there will be not much more influence of the gradients. Hence, coarse mesh has been chosen in the far away from the end, far away from the center, and the 6 centimeter from the center on the either side has been chosen with the fine mesh. So what will happen if the mesh size are uniform everywhere? There will be a lot of computational times which will waste our physical processing time. So assumption has to be considered, and I consider the properties of the temperature dependent thermal properties, and the argon gas flow is considered as incompressible and uniform flow. Okay, and the temperature distribution has been calculated by using the already available heat source model, three-dimensional canonical heat source model, and modified three-dimensional heat source model, and Dinakaran's model. These three heat source equations have been utilized to solve to find out the temperature distribution. And it is found that the Dinakaran's model is correctly predicting the temperature distribution than other two models. Okay, and the temperature see, so there is a last one, PGHS. Okay, so is the peak temperature measured by using these three heat source models, and it is found that Dinakaran's model is correctly predicting the temperature. Okay, so this is the Welding pool predicted by the three different heat source models, and the Welding pool. This is the physical Welding pool from the experiments, and the physical Welding pool measured from the experiment is correctly predicted by the Dinakaran's model. Okay. So on the temperature contours, so the parabolic fashion has been arrived by computational mechanics. We use the Dinakaran's model than others too. Okay. So this is made here. And the temperature distribution predicted by the Dinakaran's model, and see the temperature is getting constant only it reaches the quasi-static process, quasi-static, and see the temperature is maintained constantly, but when the temperature in the heat source, reaches at the end of the plate, see the temperature is suddenly rising. The reason for the suddenly increase of temperature is while the heat source is here, it will have area of normal to the surface for heat transfer, but here there will be no area further for the heat transfer enhancement. Hence, the heat is the temperature is suddenly rising from the constant to certain extent. Okay, so see this is the experimental macrograph obtained from the experiments, and these are the macro profile predicted from the computational mechanics, and see both are almost matching with the experimental results. Okay, and we have measured the results, predicted the stress measurements, and angular distortion. The distortion also predicted by using Dinakaran's model, and it is found that. So I said, analytical modeling, analytical modeling. So analytical modeling. So we have developed an analytical equation. We have developed analytical equation. So this is the a standard equation of the temperature, and I have replaced the del Q with the Dinagar's model. Del Q with the Dinagar's model. You substituted the value of del Q here. See, this is the Q naught is the uh, parameter or the equation has to be substituted from the Dinagar's model, and we have substituted in the three-dimensional triple integral, and an equation has been arrived. That equation has been arrived. This equation has been solved by using MATLAB. Solved using MATLAB, and the temperature has been arrived. The temperature distribution has been found. See, the temperature is predicted. This is one plate, and this is another plate. The temperature is predicted as like we have predicted from the experimental, as like we have predicted from the simulation. Okay, see, so we are correctly able to get this. In the experimental, the top build width is 6.6 mm, and analytical we found at 6.82, and simulated we found at 6.3, and bottom width is found at 1.4 through experimentation, and it is calculated as 1.2 and simulated as 1.7. Since the computational mechanics will be highly useful to predict the to eliminate the number of experiment types, and see the results such as the experiment XRD analysis and FEM and whole drilling method, and see the FEM method is also on bar, or the computational method is on bar predicting the results with the XRD and HDR. Okay, so this is research measurement, and fast within 5 minutes I want to wind out. I just go through the additive manufacturing. So additive manufacturing is a very cost-effective and less wastage and rapid development process. So in that, the 3D model will be developed, and 3D model will be sliced, and layer by layer, the material is ordered to generate the components. Okay, so there are different technologies. They are used in automotive industry, aerospace industry, consumer, medical, industrial, and research. And there are different processes: TDO process, laser melting, and fusion deposition modeling, clip, and the polymer, metallic and alloys, metals and alloys, powders, and thermoplastics and ceramics materials and glass materials are being utilized to produce the particular component to additive manufacturing. So I am skipping because of the time constraint, and the limitations of additive manufacturing are strength, surface finish, speed, and cost. Okay, these are the limitations of the additive manufacturing methods. And in fusion deposition modeling, so there will be a pool of material pool, and that material pool will be flowing, and it will be melted through a heat source, and layer by layer the material will be ordered like this. Okay, and it's a serial method, and so it uses the photopolymerization. This is the photopolymerization. Okay, and the material is produced. So I got some disturbance. So select laser melting. So the material gets melted, and layer by layer the material is ordered, and the required shape is being generated. So what we can see, we see the material used. So this is the distribution of material being used in the additive manufacturing, and see these components being made up of 18 parts. The component is being made up of 18 parts, but it's a fuel nozzle. But now it is made up of a single component. It's a single. We through 3D printing, it does not have any connections. It is made up of it is a single component rather than 18 parts. So, okay. So lattice structure is one of the very good area how it is being looked into. So lattice structure. So the instead of using the bulk material, you can go for lattice structure. You can go for lattice sections, and the lattice structure can be tested whether it will be able to produce the strength on bar with the bulk materials or not, that can be designed and we can go for testing. So we have used ANSYS and Abacus to get the result of a cube, of the cube of cube. It's a solid material, and we found the deformation. We found the deformation through ANSYS and Abacus. And you see, the latest section what we have, this is the physical material what we have manufactured, and the same these things have been designed in the software. ANSYS and Abacus, and we have been subjected to a compressive load. The different patterns, as like how they have designed in the physical manufacturing, have been designed in the software, and they have been subjected to compression analysis. And see, the deformation has been analyzed, and how the deformations are coherent with the one of the solid one. Okay, so by use you can avoid the lot of external trials. Okay, so there's really success, and thank you. Sir, thank you. I can take up any questions if it is there. Sorry, I have taken more time.
No problem.
Because of time concern, I wiped up this one. I wiped off additive manufacturing. So what the additive manufacturing itself,
Okay,
it will take another 1.5 hours. Hence, I have.
Sir,
Yeah.
that topic for another one day.
Sure, we will make it, sir. We'll make it one day, sir.
Okay, sir. Thank you, Professor,
Thank you, sir. Thank you.
for your knowledge on role of computational mechanics in manufacturing process with us. Thank you, sir.
Thank you, sir. Thank you so much.
Last but not least, next may I request Mr. C. Arasu, Assistant Professor, Department of Mechanical Engineering, to propose the vote of thanks. Please, sir.
Thank you, Arun sir. Yeah, very good afternoon to all. It's a great pleasure for me to propose a vote of thanks for the guest lecture on role of computational mechanics in manufacturing process. First, I express my sincere thanks to the management, principal, vice principal, and dean of academics for their continuous support and motivation to organize such technical events. On behalf of the Department of Mechanical and Automobile Engineering, and of course on behalf of all the participants, I render my heartfelt thanks to our resource person, respected Dr. V. Dinagaran, for sharing his insights on computational techniques and their roles in manufacturing process. Without any doubt, I would say that we had a great and informative session today. Thank you so much, sir. I also extend my thanks to all the participants from various colleges who made this event a grand success. And I thank all the staff members in the department to conduct this technical session in a successful manner. Thank you all.
Thank you, sir. Thank you so much. Thank you. Thanks for the opportunity.
Thank you, sir. Thank you, sir. Participants, if you have any queries in that role of computational mechanics, send the mail. You
can send mail, and or you can WhatsApp me also.
Okay.
So if you have any doubt, the researchers, those who are working on this field, you can contact me through WhatsApp, or you can mail me using the credential.